So in this lecture, we're going to explore how to do dimensional analysis. So dimensional analysis is a way by which you can figure out the units for either a physical quantity or a constant based on knowing the units of other quantities and constants in the equation. You can also use dimensional analysis to find a new equation based on knowing some general characteristics of the equation that or of the physical quantity that you're looking for. And you can also use it to figure out the values of fundamental constants by saying, okay, it should be some sort of combination of these physical quantities or physical constants that has units of such and such. So that's what dimensional analysis is used for. So here we'll start off with a very simple example. There is a very important equation in physics, which we will use quite frequently throughout this year, that the force due to gravity between two massive objects is equal to the product of the mass of the objects divided by the square of the separation distance between them. And it's also, this product is also multiplied by this constant big G, which is a constant of nature. So the question that we're going to try to find is, what are the units of this constant big G? So what that's going to entail is solving for it based on knowing that the units of force are newtons and the units of mass are kilograms and the units of separation distance are going to be meters. So here goes. So we're going to use the fact that the units on one side of an equation must equal the units on the other side of the equation, which is, you could call it the fundamental theorem of dimensional analysis. So we have the units of force equaling the units of big G times big M times, or big G times M1 times M2, or sometimes these are called big M and little m, over R squared. So the units of all those. And since these are both masses, it doesn't matter the fact that these masses might have different values. They still have the same units. 2 kilograms times 8 kilograms still has units of kilograms squared. So we're just going to get rid of the subscripts here and just combine the masses. And then we're going to take the brackets inside, which we can do. After all, the units of a product are equal to the product of the units. So what we'll do now is we'll solve for the units of big G. Remember, when you have brackets around something, that means the units of the quantity. So we'll multiply both sides by r bracket squared, divide both sides by m bracket squared, and that will solve for the units of big G. And now we're ready to plug them in. The units of force are newtons, the units of r are meters, and it's r bracket squared, so we have meters squared, and the units of mass are kilograms. So we get Newton meters squared per kilogram squared. So we can perform a similar analysis on an equation that's expressed as a sum. This is another equation that we will use a lot in this class, that the distance or the position of an object is equal to its initial position plus its initial velocity times time plus 1/2 the acceleration times the time squared. So not only must the units on one side of an equation must equal the units on the other side of the equation, but if you have an equation that's equal to a sum or difference of terms, then each term in the equation, in the sum or difference, must have the same units. In other words, x naught has the same units as x, and they also have the same units as this v naught times t, and they also have the same units as this 1/2 at squared. So based on knowing that the units of x are going to be meters because it's a position, then since we know that the units of time are seconds, and this is seconds squared, then in order to get units of meters out of this, then the units of acceleration must be meters per second squared, so that the second squared from time squared ends up canceling that. So now we know the units of acceleration. Similarly, we also know that the units of velocity are meters per second because we need units of meters out of this, and we have 1 power of seconds from the time. So units of time are seconds, so units of v naught must be meters per second, so the meters per second times seconds equals meters. So now let's look at an example that you all will finish for homework, in which we try to actually derive the smallest sensible unit of length. There are a number of derivations in fundamental physics that show that the smallest sensible unit of length is the correct combination of Newton's gravitational constant, big G, which we just looked at, and the speed of light, and h bar, which is the Planck's constant from chemistry divided by 2 pi. It's actually twice the fundamental unit of angular momentum in quantum mechanics. But the point is, it seems that the smallest sensible unit of length is going to be some combination of big G, c, and h bar, or at least it's going to be within that order of magnitude. Question is, what combination? Well, it needs to be whatever combination ends up yielding units of meters. So we have big G to some power times c, the speed of light, to some power, some other power that is, times h bar, Planck's reduced constant, to some other power, is going to have units of length, which are going to be meters. So we don't know what the powers of p, q, and r are, but we are going to solve the equation that we're eventually going to get to figure out what they are. So the point is, we're going to plug the units for big G in, which turn out to be meters cubed per kilogram second squared. That's the same thing as the Newton meter squared per kilogram squared that we just derived. And plug in the units for speed of light, which are meters per second. Plug in the units of h bar, which are kilogram meters squared per second. And we're going to raise them to these powers. And the point is that at the end, we should only have units of meters left over. And the only way we can do that is if, after we rearrange all of our exponents and apply the power to everything that's inside of it, we end up setting the final exponent for meters equal to 1. And set the final exponent for kilograms equal to 0. After all, you don't see a kilograms here, but you do see a meters to the first power here. And set the final exponent on seconds equal to 0 as well. After all, there aren't any units of seconds here. Now, if we were trying to derive the smallest sensible unit of time, then we would set the units of seconds equal to 1, or the power of seconds equal to 1, and these other powers equal to 0. But we're not. We're trying to get a unit of length. So we're going to do this based upon knowing these values. In fact, since I originally made this slide, the value of big G has been revised downward slightly. We now think it's more like 6.6738 times 10 to the minus 11. But we're not going to let that concern ourselves here, because the whole derivation only gives us the smallest sensible unit of length, really, to within an order of magnitude. So we'll see how that ends up working out. Actually, you all will, because you're going to finish the derivation for homework. So the point is that when you plug in the units of big G, you get meters cubed per kilogram second squared, raised to some power, which we called p. When you plug in the speed of light, the units for the speed of light are meters per second. The numbers don't matter for us right now. The numbers, they go away, because the units are the same regardless of what the number is. And the units for h bar are kilogram meters squared per second. We raise that to this new power r. And we're trying to get units of length, which are meters. So now we're going to distribute these exponents through all of these quantities. So for example, this will become meters to the 3p over kilograms to the p seconds to the 2p, all in the denominator, with meters to the 3p being in the numerator. This will become meters to the q over seconds to the q, and this will become kilograms to the r times meters to the 2r over seconds to the r. And all of that's got to be equal to meters. And again, meters is really meters to the first power. And since we don't have any kilograms or seconds here, but we have them here, we'll just say, okay, that's kilograms to the 0 power times seconds to the 0 power. After all, that's 1 times 1, which is just still leaves this unchanged. So anyway, after we distribute our p, q, and r to these units, here's what we obtain. We get the meters to the 3p over kilograms to the p, seconds to the 2p, meters to the q over seconds to the q, and kilograms to the r, meters to the 2r over seconds to the r. Again, you should just verify that elementary math here. Now, we want to rearrange all of these things. We want to get all the meters together, get all of the kilograms together, get all of the seconds together. So that's what we've done. We've just rearranged this to pull all of these together and kept the exponents that were on them. And remember, a product of numbers that have different exponents but all the same base is just equal to the sum of the exponents. And if it's a division, then it's the difference. Like we have kilograms to the r over kilograms to the p, that's just kilograms to the r minus p. Very basic stuff. So when you do this, here's what you get. Well, remember, we're trying to get units of meters here. Well, there's our exponent for meters. 3p plus q plus 2r must equal 1. See, there it is, meters to the first power. So this exponent must equal 1, because we're trying to get units of meters. Kilograms exponent must be 0. There aren't any kilograms here, so r minus p must be equal to 0. And the seconds exponent must equal 0, because again, no seconds here, so negative 2p minus q minus r equals 0. So when you write all of those down, here's what we have. Aha! We have a system of simultaneous equations. And the first thing that you can do here is realize from the second equation that since r minus p equals 0, that means that r equals p. So remember, the general way of solving any set of simultaneous equations is to solve one of the equations for one variable and plug that variable into each of the remaining equations. And again, keep this in mind because you're going to be doing a lot with simultaneous equations, especially when we get to Newton's laws. So hopefully you are relatively good with simultaneous equations. So we're going to realize that r is equal to p here. So in the next step, everywhere we see an r in the remaining equations, we're going to plug in a p because that's what r is equal to. So here we go. There used to be an r here. Now we've plugged in a p. There used to be an r here also. We've plugged in a p. And after rearranging these and combining like terms, we now have a set of two simultaneous equations with two unknowns. 5p plus q equals 1, negative 3p minus q equals 0. Now we can use a trick with simultaneous equations. It's always okay to add and subtract true statements. These are true statements. So we're going to add these together. The reason we're going to do that is because we notice we have a plus q here and a minus q here. So when we add them together, that will just cause the q's to cancel. And we'll get that 5p plus negative 3p is 2p. Q minus q is 0. That's the whole point of doing that. And 1 plus 0 is 1. So we get 2p equals 1. So apparently p equals a half. And we already realized that r is equal to p, so now we know that r is equal to a half as well. So based on that, you can plug your numbers back into the original equations and find out the value of q. And once you've done that, you will have values for p, q, and r. You're still not done though. Now, based on that, you go back to here and plug in the values of big G, C, and H bar using the exponents of P, Q, and R that you just found. For example, you know that P and R are both equal to a half, and I'll let you figure out what Q is. So you plug in the numbers for big G, C, and H bar that we have right here, raise them to these exponents P, Q, and R that you found, and find out what that final number is. I'll tell you right now that it's on the order of around 10 to the minus 35th meters, but for your homework you need to solve for what that exact number is. So that's the end of our introduction to dimensional analysis, and I'll let you do the rest on your homework.